Hello again, this is the Pencrest High School AP Physics C video series. This is video 3A, Introduction to Work and Energy. So once again, there's good news concerning work and energy. Most of the concepts from last year are coming back. Most notably, the three forms of mechanical energy, that is kinetic, elastic potential, and gravitational potential energy. The work done by an applied force, the work done by friction, elasticity, power, and the conservation of energy are all critical concepts that are going to be coming back this year. We are going to be introducing some new methods to quantify some of these, in particular work done by an applied force. We're also going to look at a new way to approach energy conservation that's called the work and kinetic energy principle. We're also going to look at graphical representations of energy as a function of position, and the concept of conservative and non-conservative forces is also going to be introduced. So we're going to briefly summarize the quantities and the symbols and formulas and so on for each one. Capital K is kinetic energy, just as it was last year. 1/2 mv squared, where m is the mass, v is the velocity. U sub g, capital U sub g, is the gravitational potential energy. Generally speaking, this is listed as delta U sub g equals mg delta h, where m is the mass, delta h is the change in height. You might remember mgh from last year. One of the things that we did last year was establish where h equals 0. And we said that we would normally make that the lowest point that the object would reach, and this way mgh would never be negative. What we're going to find now is that the change, the delta U sub g, where we have mg delta h, where h equals 0 becomes irrelevant. So we look basically at delta h, which is the change in height. We look at where it was at the beginning and where it was at the end. And that delta h change in height is what we're concerned with, not necessarily where h equals 0. For U sub s, elastic potential energy, 1/2 k delta x squared. We saw that last year as 1/2 kx squared. The delta x, of course, is the deformation of the spring. No real difference there. Notice that those three formulas, k, delta U sub g, and U sub s, are all on the formula sheet. When we look at the two work done formulas, we had a formula for the work done by an applied force, FAD cosine theta, where FA is the applied force, D was the distance over which it acted, and theta was the angle between the force and the distance, or the displacement, I should say. You'll notice that this formula is not on the AP Physics C formula sheet. So it's in a blue box. It's a good one to remember, but there is another version of it that we're going to be a little more familiar with. The work done by friction is the same as it was before. Mu times Fn times d. That negative sign just indicates that more often than not, the work done by friction will be negative. It's removing energy from the system. So now these formulas look a little different from last year's, but the general premise is going to be the same. So we're still going to be approaching this from the idea of the conservation of energy, but we're going to look at it a couple of different ways. Okay. So the way we looked at this last year, we looked at two locations in time and space, point A and point B, and we said that the energy at A, plus or minus the work done, equals the energy at B. Now this, of course, energy at A and energy at B are the total mechanical energies at points A and B. So the total combination of kinetic energy, gravitational potential energy, and elastic potential energy, if they all exist, they could conceivably be different at points A and B. When we approach this from the premise that energy is conserved, we would say that the energy at A equals the energy at B, unless, of course, there's work done in between. So we have an FAD cosine theta. This would be work done by an applied force. We could conceivably have work done by friction. There's the work done by friction term. Worst case scenario is that all 8 terms are present in any one situation, however unlikely that may be. So the first thing we'll look at is the concept of work done. The 3 forms of mechanical energy are no different than they were last year. So if you feel like you need a refresher, the place to look would be not only in the blue book from AP Physics 1, but also the AP Physics 1 video series where it has quantification of work and energy. So that's where we would want to look if you feel like you need a refresher. Okay, so that's it for the intro. The first thing we'll look at will be some new versions of how to quantify work done. And then we'll look at some of the other stuff a little later on. So until then,